I was creating an export tool a few months back inside Houdini, and one of the problems I first faced was, how can I allow the tool to accept various possible inputs and present the user a UI that is configured solely for the input geometry? And to that, I solve it using dynamic UIs. Let's imagine a scenario. We have a bunch of points, and the points have an attribute called letters. In our HDA, we want to look at a list of unique letters and create a float slider for each letter. Well, if we already know that there are A, B, C, and D unique letters, we can manually just create 4 respective float sliders. So what's the problem? Well, if we were to switch the input and now we have an E and F attribute, we don't want to go back to the tool and create float sliders for the 2 additional attributes. We want our tool to be smart enough to create these sliders itself. Alright, let's go into Houdini and set up the scenario. Drop a geometry node, dive right in, create a sphere sort, scatter some points. For this tutorial, let's keep it to 10 points for now, so we can view the geometry spreadsheet a little easier. Let's drop down a point wrangle, and I'm going to type the code in the text editor, just so the words are bigger and easier to see. And I'll just copy and paste the code into the wrangle. You can type directly into the wrangle itself. We first want to create an array of letters to choose from, so as to allow us to create various random inputs later to test our HDA better. I'm going to separate each letter with an underscore, so I can easily create a string array by using the split function. What it does is that it takes the input string and splits it into an array whenever it encounters an underscore for our case. So now we have an array. It is time to assign random letters in the array to our points. We create 2 sliders, one which indicates from which index we start to choose from, and the other indicates the last index we can choose from. We use the random function based on the point number, and we feed it to the min and max range that is indicated on the slider. We then typecast the value to an integer and use it as the index to select the appropriate letter in the array. And with that, we have our attribute set up. Now we just drop down a null at the end, and this would be the input to our HDA. Now remember what we talked about at the start. We wanted to create float sliders for each unique letter. So in our HDA, that is what we have to process. Drop down another point wrangle. And for this part, we want to run through all the points only once and not in parallel. For that, we switch the wrangle to detail. Call it detect unique. We drop down an output for good measure, and that will be our basis for our HDA. Now, let's write the code in the wrangle itself. For that, I'm going back to the text editor. We first grab the total number of points using the endpoints function and create an empty array to contain our unique letters. We use a for loop to iterate through all the points, and for each point, we can use the find function to see if the current processed points letter is inside the unique letters array. If it is not inside, the function would return a negative number. So if it's below 0, we append the letter to the array. We finally assign this array to a detail attribute called unique letters, and that's all we have to do. Now, let's grab the 3 nodes and create a HDA out of it. We'll call it dynamic UI, and we got ourselves a HDA. So inside the HDA, there is the scripts tab, and here is where all the magic happens. We can write all kinds of customizable functions to further level up our HDAs. We are going to select the Python module, which allows us to store Python functions where we can access functions anywhere from the HDA. We're going to create 3 buttons, and we're going to name them Method A, Method B, and Clear. The reason for the Method A and Method B buttons is because we are going to explore 2 ways to create dynamic UIs. And the Clear button is there to clear out our dynamically created UI. Just keep that in mind, and it will get clearer as the lesson goes on. Now, a little introduction to Python in Houdini for those who have not used Python in Houdini before. One of the easiest ways to test out snippets of code is by using the Python shell. Let's try to first use the shell to see if we can get our detail attribute containing the unique letters. We create a variable called node, and we can click on our HDA node and drag it into the shell. As we can see, our HDA node is now assigned to our variable, and we see that the node is an object of the who.subNode class. So with this information, what we can go about doing is Google search who.subNode, and we can see a list of functions we can use. The node is currently referring to the node itself and not the geometry data. So to grab the data itself, there is a geometry function in the class which returns a who.geometry. And if we look at the documentation for who.geometry, we can see that there's a function called string_list_attribute_value. That is what we need, because what it does is it returns a detailed string array, or in Python's case, a list. So let's just do those steps in the Python shell. We grab the geometry by calling the geometry function, as we've seen, and we get the detail attribute by using the string list attribute value. And from the Python shell itself, we can see that the return value corresponds to the detail attribute in the geometry spreadsheet. Since everything is working, let's now get back to the HDA's Python module and type out some functions to do just that. I'm going back to the text editor first, so it's easier on the eyes. We create 3 functions, Method A, Method B, and Clear. All of them would require a reference to our HDA node to work, so let's add node to our function parameters. So we are going to do exactly what we did in the Python shell. Get the geometry, get the list, and assign it to a variable called letterList. So a little bit of prep work. We now have our buttons, our Python module, and our functions. What we want to do now is that when we press the button, we want to run a callback script to access the Python module, and from there, we want to call the functions inside it. So in this tutorial, we are going to explore 2 ways to access this function in the Python module. One, which is the who.phm, or Python Houdini module function, and another is the keyword arguments, or quarks method. Essentially, quarks and square bracket node refers to a reference of the current node. And from the node itself, we can call the HDA module using the HDA module function. Let's link the buttons to the respective functions. I'm going to type the various callback scripts for the buttons in the text editor first, and then I'll show you where we can type these lines of code in the HDA to link the buttons to the functions. For button A, let's try the who.phm method. The syntax would be who.phm dot method A bracket quarks square bracket node. The reason we put quarks square bracket node inside the function is because the function that we have written requires a reference to the node as a parameter. Alright, for button B, let's try the quarks method. So quarks square bracket node, which means a reference to the current node, dot HDA module dot method B, open brackets, quarks, square brackets, node. And for the clear button, let's just use the PHM method because it's shorter. We go back to the HDA and we click on the buttons. In the callback script, we can paste the respective lines in it. And remember to switch the line to Python, as by default it would be HScript. The callback script would be run whenever we press the button. Finally, I'm gonna start pasting the code that I have written in the Python module. Good. Now let's print out tests to the Python editor whenever we press the clear button. Let's press the button and looks like there's an error. The reason for that is because I forgot to type the colon next to the clear function. And now when we press it, yay, it works. Let's finally get to the meat of the tutorial, dynamic UIs. I'm going to go over two methods. Method A revolving around the add spare palm tuple function, and method B around the palm template group concept. Now back to the Python module. We will go through each letter in the letter list, and we'll create a floating parameter using the who.floatPalmTemplate function. This function requires only 3 compulsory parameters: the name, the label, and its size. The rest are optional, and you can find out more by looking at the documentation online. We then assign these parameters to the node using the add spare palm tuple function from the node. For method B, we are going to explore the palm template groups. Essentially what it does is that it allows us to grab the current parameter definition of our HDA. And after grabbing it, we can modify it and then finally reassign it back to the HDA node. So we create a variable called group and assign the node's parameter definition using the palm template group function. Again, we look through the letter list and create a float parameter for each letter with the who.floatPalmTemplate function. We then append this parameter to the group using the group's append function. Once we are happy with the edited palm template group, we can reassign it back to the node with the node.setPalmTemplateGroup function. Oops, looks like we have an error, and that is once again because of the clear function. For now, I'll just put a pass. And as you can see, when we click the button, we are creating the float parameters. But wait, if we were to click the button again, we see an error pops up. This is because in a HDA, every parameter has to have a unique name. And what we are trying to do is we're creating this parameter with the same name as an existing one. Even if we were to manually try to create a parameter with the same name, as you can see, Houdini doesn't allow that and automatically renames the parameter. For the sake of this example, what we can do as an easy solution is we can use the clear button to run the clear function to clear the parameters. Whenever we create these dynamic parameters, what we are essentially creating is spare parameters. So what we can do to remove it is just called the remove spare palms function. And once that is applied, you can see that the node is now working. Now here's a little something extra. Let's create a float parameter and a folder. Put the float parameter inside the folder, and we shall name our folder my splendid folder. Alright, so now if we create the UI dynamically, it will create the parameters below the current UI. So what if I want to create the parameters specifically in the folder? Well, going back to the documentations, we see add-spam palm tuple has a second parameter which is called inFolder. What it allows us to do is specify a folder to put the parameters in. And the third parameter asked is if we would like to create any missing folder if the folder in the second parameter is non-existent. One gotcha is that the second parameter requires a sequence of folders. And as shown in the example, if we only have one folder, we still need to put it in brackets and add a comma at the end. Now, let's modify our functions to allow us to put parameters in the folder. We input the label of the folder UI instead of the name of the folder UI. And that was the reason why I gave that ridiculous name, just to drive home the point. For the palm template group, instead of the append function, we can use the append to folder function instead. Just going to get the commas right. Copy, paste, and there we go. Our UI is created inside the folder. So now you may ask, why method A and method B then? Both seems to be working, both seems to be giving the results that we want. Well, to illustrate this, as well as to exercise my drawing skills, let me explain using a story and an illustration. Imagine we have a little monkey. This little monkey starts writing some parameters, and my oh my, he has a tons of it. So the little monkey grabbed all the parameters and head towards the HDA. Now let's look at what the monkey does for method A. The monkey reaches to the top of the stack, and lo and behold, he grabs but one parameter, opens the HDA, throws it in, and shuts it. He then grabs the next parameter, opens the HDA, throws it in, and shuts it. Grabs the next one, opens the HDA, throws it in, shuts it. Can you imagine how tedious this process could be? Now, for method B, the monkey opens the HDA, grabs not one, but the entire stack, throws it into the HDA, and smashes it shut. The end. Similar to the monkey, each time we call add-spam palm tuple function, Houdini has to make an IO call to write the parameter and then save it. Whereas for set palm template group, we can get the entire parameter definition and edit whatever we want to it, and then put it back to the HDA in a single call. For the sake of proving how different the speed can be, let's modify the code a little. By the way, you don't have to follow this part of the tutorial. Back to the Python module, let's import time and create a timer at the start and at the end of the methods and print out the elapsed time. Let's open the Python shell as we will be printing the elapsed time to it. And before that, dive into our HDA to modify the VEX code a bit. Let's emphasize the speed difference by creating a whole lot of other extra parameters. We use a for loop to create 400 parameters. And we can then use the sprintf function to create a string instead of printing the output out. Now, let's try method A. And that took 3.65 seconds. And what about method B? Well, 0.016 seconds. That is more than 200 times faster. Of course, this gets more obvious the more parameters you have to create. Alright, so finally for the last part. At the moment, our HDA isn't as dynamic as we hope to be yet. It still requires us to press buttons to populate the UI. What if we want to take a step further and create the UI upon the input change? Well, we can do just that. Let me just delete the extra lines of code first to get back to where we were before. Now let's create two inputs. On the left, we have a node that creates two parameters. And on the right, we have a node that creates 7 parameters. Okay, so in the HDA, under the script section, apart from the Python module event handler, there are many other event handlers we could choose from. And what we want is the onInputChanged event. And let's tell the HDA that when our input changes, it should first run the clear functions to clear our spare parameters and use method B to populate our parameters. Click apply and see if it works. Well, the parameters are indeed being updated upon the input change, but look at what we have here. The left node is supposed to have 2 parameters and the right node is supposed to have 7. So why is it that the right node is creating 2 parameters and the left 7? Well, let's run through the order of events. We have our HDA, and with it the input data entering the nodes inside the HDA. We have 2 imaginary nodes. One has 6 unique letters and one has 4 unique ones. Prior to this, input 1 was connected and so 6 float sliders were created, and the input data inside the HDA reflects the same. Alright, so now we switch to the input 2. So in our script section in our HDA, we tell it some instructions to do upon the input change. We tell our HDA to clear the parameters, populate the parameters with the current data, and only then would the nodes inside the HDA gets cooked and or updated. Instead, what we would want is, upon switching, the HDA should first grab the data and process it. Then we clear the parameters, and then we populate the HDA with the newly processed data. So now we got it all figured out. Let's go back to Houdini to implement that. So as Quark's node is a sub node, let's look at the documentation. Inside we can see there's a node function that returns the node at a given path. So with this we can grab any node inside the HDA. We then dive further and we see that the return node has a function called cook, and we can force it to cook. Cook means update. So we can type quarks node dot node input. The reason for input is because the node in our HDA is called input. Dot cook force equals 1. And now if we apply it, we can see the left node creates 2 parameters and the right creates 7, which is correct. And that concludes the tutorial. Thank you for listening, and I hope this has been helpful to you. If you have any feedback on how I can improve the setup or the tutorial itself, please feel free to let me know. Thank you and goodbye.